Okay, so in this example, one thing I wanted to show about the eigenvector centrality values is this. The definition of eigenvector centrality is a measure of the degree of the vertex as well as the degree of its neighbors. So if you look at it, so the largest eigenvector centrality values is for vertices 0 and 2, so it is 0.489. Okay. So you see 0 and 2 are kind of not distinguishable from each other based on degree. They each have degree 3, and two neighbors are 1 and 3. So there's no way we can distinguish 0 and 2. So that's why they have the same eigenvector centrality. But the other vertices, they have different eigenvector centralities, and again 6 and 7, they are not distinguishable from each other because they have a degree of 2 and their common neighbor is 5. So there's no way they can have different eigenvector centralities. So if you want to now rank the vertices based on the eigenvector centrality, you will choose the largest eigenvector centrality first, which is 0 and 2, and then you can rank the others. Now one thing you should also notice here is, so as I said earlier, having just a larger degree is not sufficient for a vertex to have a larger eigenvector centrality. So vertex phi has degree 3, which is same as that of 0 and 2, but 0 and 2 have a much larger eigenvector centrality of 0.489 compared to vertex phi, which has 0.232. And the reason for a low eigenvector centrality for vertex phi is, even though it has a larger degree, its three neighbors have a lower degree. So 4, 6 and 7, they have degree 2. Whereas for 0 and 2, 3 has a relatively larger degree of 3, 2 has a larger degree with respect to 0, and 1 has a degree of 2. Similarly, with respect to 2, 0 has a larger degree and 3 has a larger degree. So 2 of the 3 neighbors have a degree of 3, whereas for vertex phi, all the 3 neighbors have a degree of 2. So that's kind of implicitly captured when you can compute the eigenvector centrality. Okay. Now vertex 1, it has a degree of 2, whereas 6 and 7 also have a degree of 2. But you see, 1 has 2 neighbors, both have degree 3, whereas 6 has 2 neighbors, one has degree 3, other has degree 2. And not only that, 0 and 2 have larger eigenvector centrality. So the degree of the neighbors is captured, and kind of as part of it, the eigenvector centrality of the neighbors are also implicitly captured. So 0 and 2 have a larger eigenvector centrality, so 1 has a reasonably larger eigenvector centrality. Whereas 5 and 7 have a lower eigenvector centrality, so 6 has also a lower eigenvector centrality. So all these things are kind of interconnected to each other. But at the end, what we have is just one single metric value that comprehensively captures all this stuff. Okay. Alright, so any question on eigenvector centrality? We'll look at these two examples quickly. Okay, so let us go over those two examples and move on. Alright, so given a graph, the first step is to come up with the adjacency matrix and then multiply that with the unit column vector of all ones, and it's simple matrix multiplication. So to get this index corresponding to row 0, column 0, so the entire thing is column 0, the first column. Multiply that row 0 with that column. So 0 times 1 plus 1 times 1 plus 0 times each of those ones, so that is 1. For this entry here, that is row 2, column 1, so this is a row multiplied by this column. So 1 times 1 plus 0 times 1 plus 0 times 1 plus 1 times 1 plus 0 times 1, so that's 2, and so on. So once you get that, the product vector, you have to normalize it. So for normalization, find the square root of the sum of the squares of the entries here. So it's 1 square plus 2 square, which is 5, plus 2 square, that is 9, plus 3 square, that is 18, plus 2 square, that is 22. So square root of 22 is 4.69. So that's the normalized value. Then divide each of these entries by that normalized value for 4.69. So 1 divided by 4.69 is 0.213. 2 divided by 4.69 is 0.426, and so on. So that's our kind of column vector at the end of the first iteration. So now for second iteration, use that column vector instead of the unit vector of all ones to multiply with the adjacency matrix. And again, you have to multiply the adjacency matrix times that column vector like this. And this is the product vector. So it's 0 times 0.213 plus 1 times 0.426 plus 0 times each of this. You get this 0.426. And then normalize this. So take the squares of these numbers, some square root of sum of these squares, and that is 2.19. So divide each of these entries by 2.19, we get these numbers. So they have not yet converged. Our criteria uses based on the normalized value. It was 4.69 in the first iteration and 2.19 in the second iteration. So let us do the third iteration. So use this column vector and adjacency matrix to multiply, and you get the product vector. So normalize this, you get 2.21. So divide each entry here by 2.21, you get entries like this. Then use this column vector to multiply, you get 0.352 and all these things, and the normalized value is 2.21. So we can divide each of these by 2.21 and you get these numbers. So this is the final eigenvector centrality of these vertices. Now one property, it's interesting property of eigenvector centrality. Of course, you see all the entries are between 0 to 1 in the eigenvector centrality, and also it is already normalized. So you all know by now what I mean by normalization, right? So we take, say for example, the square root of the sum of the squares, and then you get a normalized value. Then divide each of this by that normalized value to say we have normalized this vector. Now if you do that same kind of calculation with the eigenvector centrality values, you will get the sum of the squares to be 1. So if you multiply 0.7176, if you square it, plus 0.352 square plus 0.484 square plus 0.616 square plus 0.484 square. So the sum of the squares of the eigenvector centrality values will be 1, and the square root will also be 1. Square root of the sum of the squares is going to be 1. So then if you divide each of these entries by 1, which is the normalized value, you just get the same thing. So that's a good property of eigenvector centrality values. They are already normalized. Okay. So that's the second example or third example which I let you to practice this. So once you get the eigenvector centrality values, if you want to rank based on the largest values. Always in the module we'll use the larger the centrality metric value, the higher the rank for the vertices. So 0.632 is the largest one, so that is for vertex 4. So that's ranked first, and then the next largest is 0.494 for vertex 2, then 0.376 for vertex 1, 0.297, 0.297, 5 and 6. So if two vertices have the same score, then we break the tie based on the node ID. We will also look at some other way to break the ties more formally, but if I don't ask you to do all those things, just break the tie based on node ID. And then 0.198 is the smallest, which is for vertex 3. Okay, so any question on eigenvector centrality? Okay, so let us save this video.